We're looking at Chapter 5, Clausius Inequalities. And in our Clausius Inequalities, we're going to be looking at a cycle, and if it's going to take in energy or give off energy. And it doesn't necessarily have to be between two thermal reservoirs, but just the energy going in and going out. So our Clausius inequality, we're looking at our sigma here, and we have this integral, right? And it's a cycle. So for example, like if and I'm not looking at this Clausius, say I have this system right here, and 1, 2, 3, 4, 5, 6, it's not a very good point, but 7, okay? And so say I'm just looking at Q cycle for this. And so if I'm looking at our Q cycle, so we're looking at the partial integration of Q over the entire boundary. Okay, so we're looking at the entire boundary, and we have 7 steps. And so basically with this cyclic integration is that we're looking at the integration from 1 to 2, with Q 1 to 2, right? Plus 2 to 3, plus all the way around till we get to going from 7 back to 1. So we're looking at the whole boundary, okay, for a particular cycle, for example. And so that's what that integral with the circle, the entire cycle, and B is for the boundary. So when we look at this Clausius inequality here, we're looking at the nature of the cycle. It's executed. Okay, and we're going to compare it that if our sigma cycle is equal to 0, then there are no irreversibilities present in the system. It's reversible, basically. If the sigma cycle is greater than 0, we have some irreversibilities present, and if it's less than 0, it's an impossible process. So when we look at this, because like in our Carnot cycle, we have two, in our Carnot cycle, we have two adiabatic processes and 2 isotherms. Correct? When it's adiabatic, we know Q is 0. So with those isotherms, heat is going in and heat is coming out. And so when we look at our calculating for our sigma cycle, our inequality, our Clausius inequality here, for our Carnot cycle, for example, right, if we draw our Carnot cycle for a gas, I'm going to try to draw this, right, 1, 2, 3, 4, and the 1 to 2 is adiabatic and 3 to 4 is adiabatic. So these isotherms are these lines here. And so when we're looking at our 2 isotherms, Q for the coming in from the hot temperature, if we're looking at a power cycle. So for our Clausius inequality here, we have for our Carnot cycle, right, we have an QH over TH plus we have QC divided by TL or TC. And a lot of times Q is a negative value, right? Because that's where heat is coming out. So a lot of times you'll see this written as QH minus TH minus, and that is that negative sign that comes with the heat coming out, Tc, for this process. Okay, but remember, as Q, if you keep the sign, if you leave it as plus, because we're summing up all the integrals, QC will actually have a negative sign on it. So let's try this out. We have an example 4, and we have a system that undergoes a cycle, which receives 1,000 kilojoules of heat transfer at a temperature of 500. So I'm just going to draw this just because I'm just going to keep everything in mind here. This is 500 K, and we're going into our system, and we have QH, which is 1,000 kilojoules, and we have Q going out, QC is discharging 600, and our low temperature is going to be, depending on what we have, 200K. Our second is 300K, and our fourth is 400K. All right. So we want to know the nature of the cycle for each one of these cases. So we're going to find our Clausius equality. And right, that is our Q over T for the boundary. And in this particular, we have just two systems, one going in and one going out. So we have our Q from the high, and we have Q from the low. Okay, and then we're going to calculate C. So let's look at this for A. So our Clausius equality is going to be 1,000 kilojoules divided by 500 minus, because I'm taking account that minus 600, or I can leave it here, 600 kilojoules all over 200. And we can, if I bring my sign over, 1,000 divided, or 5, this is 2, minus 3, this, right, 2 minus 3 is minus 1, but there's a minus here, this is 1. Since this is greater than 0, right, if it's greater than 0, we have some irreversibilities present in our system. For B, we're going to do the same thing. We have 1,000 over 500. Now our temperature is going to change here. We have 600 over, and we have 300. And again, if I bring my sign over, right, this is still 2. 6 divided by 3 is now also 2. And this is going to be equal to 0. If this is equal to 0, then this is a reversible, right? Reversible system. Or no reversibilities. Okay. And then C, you can see a pattern here. We have our QH over TH, and now we're doing Q cold over our 400. And so here we have, my sigma is not very good. 2 minus, so we have 2 minus 1.5, and that is equal to, this is equal to 0.5. But there's that negative sign here. And so since this is less than 0, this is, this is impossible. Our cycle will not work. Or our power cycle is not going to work because it's, we can't have a Clausius inequality to be greater than, or excuse me, to be negative. It cannot be negative.